Thanks very much. Yeah, so here's the goal. We've got 2 lectures left. The goal is today to do compact semi-simple quantum groups, and on Friday, complex semi-simple quantum groups. And I've taken, as a point of arrival on the 2 days, the Plancherel formula, which is a classic result in representation theory for any group or quantum group. It's something you might want to know is how to decompose its L2 space into irreducibles. But really the moral of the talk is the way the classical world deforms into the quantum world and what techniques you need to understand that. So I know probably most of the audience already knows this stuff, but I think for the few people that are not specialists in quantum groups, it's worth just repeating this stuff, which I'll do very quickly with a few slides at the start, which is the motivation of where quantum groups come from. And here's the philosophy. So you start with a group. Maybe it's a topological group, maybe it's a Lie group, maybe it's an algebraic group. I don't really care for the moment. It's just philosophy. And the point is that with a group, you can make 2 types of algebras. The first are functions on your group with pointwise multiplication. So this is just seeing the group as a topological space, if you like. And so I've given some examples here: C0 of G, L infinity G, the Fourier algebra A of G. Okay, probably name some others yourselves. The other type of algebra that you can make is a convolution algebra, which needs distributions, not functions. Distributions naturally convolve with each other. Your distributions might be smooth, so they might come from functions multiplied by a measure, but they will be canonically distributions, and they can be convolved in these various ways. So you can get C star of G or L1 of G, or a good example is U of G, the enveloping algebra, which is distributions supported at the identity element in the group. These are all convolution algebras of distributions, and they only see the group structure. They come just from linearizing, if you like, extending linearly the group law. Okay, so just to make this extremely clear, these 2 algebra structures that you get on a group come from 2 operations on a group. The first is the group law, multiplication, and the second is the much underrated diagonal map, which embeds G into G times G along the diagonal. Okay, and if you use either the push forward by multiplication on distributions, you get convolution, or if you use pullback on functions by the diagonal embedding, you get the pointwise multiplication. Okay, and this is a recurring theme. Functions like to be pulled back, distributions like to be pushed forward, and to do the wrong way, you basically need to convert your functions into distributions before they will allow themselves to be pushed forward. So one famous thing about abelian Lie groups is that you have a Poincare duality, which converts convolution into pointwise multiplication. So at a very formal level, here's the way you might strategically decide to prove Poincare duality for a group. We'll start by just formally renaming our distribution algebra, which I call D of G, as A of G hat. There I've done nothing but rename it. Okay, it's just a new name. But then I want to deduce the existence of some underlying group G hat, perhaps by Gelfand's theorem about spectra of abelian C-star algebras, for instance. Deduce that there exists some topological space G hat underlying this algebra A of G hat, and then show that that exhibits itself a group law, and then I get my Poincare dual group. Okay, but in order for this to make sense, I need that the category of my AGs and my DGs are the same, so that I have a reasonable chance of finding a group G hat whose AG hat is equal to my D of G. So let's just check the basic properties of groups. The first is associativity, and let me just point out that as multiplication is associative, that you all know, so the diagonal embedding is co-associative. If you take the element G, you split it into G, G, and then you split that into G, G, G by either splitting the first or the second variable, you always get G, G, G. So this is a co-associative operation. On the other hand, as you are no doubt expecting, commutativity is not the same. So while multiplication isn't always commutative, the diagonal embedding is always co-commutative. You always get GG. If you flip GG, you still get GG. Nothing non-commutative or non-co-commutative can happen. And this is why Poincare duality doesn't work for non-abelian groups. So if you want to have Poincare duality, you've got two options. Either you restrict your attention to the abelian groups. Sorry? I can't hear. Oh, Pontryagin. Sorry, I've got the wrong P mathematician. Excuse me. That should have always been Pontryagin. Right, let's try again. So if you want to prove Pontryagin duality, then you have two options. The first is you restrict your attention, which is kind of sad, to abelian groups. Or the second option is to invent non-co-commutative groups, and that's what a quantum group is. Okay, and there's no universally accepted definition for what a quantum group is, except that it always involves some operations which are group-like and some co-operations which are co-group-like. So there's some kind of Hopf algebra structure going on, and then how you interpret that technically depends on your personal preferences. And we're going to talk about a bunch of these. So let's just remind you what the definition of a Hopf algebra is. The correct definition you will find on Wikipedia, of course. But in short, a Hopf algebra is given by a product and a coproduct, a unit and a co-unit, and an antipode, which is supposed to be the equivalent, the algebraic equivalent of the inverse. And the two classic examples is if you take a finite group G, then you have 5 maps on this group. You have multiplication, the diagonal embedding, which we've already talked about. You have the inclusion of the identity element from the trivial group. You have the quotient to the trivial group. And you also have the inverse map, which maps G to G op. And if you use those 5 operations with pullback of functions, you get A of G, functions on the group with multiplication. And if you use them with push forward of distributions, you get D of G, distributions, if you like, on my finite group. I mean, they just look like functions again in this case, but with convolution instead of pointwise multiplication. Okay, so that is the philosophy. Now we need to put that into practice. Any questions on the philosophy part? No religion today. So. Good? Yeah, so we can turn that off unless people want to continue gazing that, pondering. I'm going to move to the blackboard. So as I said, the universal enveloping algebra is an algebra of distributions supported at the identity element. And it's given by convolution. It's got a product given by convolution. And what's more, as a coproduct, so we've already talked about the product, that was Monday. The coproduct is as follows. So the coproduct is supposed to be the diagonal embedding, push forward of my distributions by diagonal embedding. And since my elements of this Lie algebra are given by differentiation, you need to just figure out how you differentiate a function along the diagonal. And all you do is you differentiate along the first variable plus differentiate in the second variable. It's the Leibniz rule. And that works for everyone. I'm going to restrict attention as usual to SU2. So for every one of these 3 basis directions, I do the Leibniz rule, and that's a Hopf coproduct. And the co-unit and the antipode you can look up. Let's not bother with those. So the physicists discovered that not only does the algebra UG quantize, so does the coalgebra. And I just want to make sure I keep my conventions because there are various different possibilities. All you do, put a q to the h there and a q to the minus h there. Or if you're a K lover, that's a K and a K inverse. If you're a K lover, you don't let me do that. You need to take Q to the power of that. Oh, what have I done? Sorry, getting distracted. It should be H maps to. And here there should be Q to the H mapped to Q to the H, tensor Q to the H, which is just the exponential of that first rule there. Okay, and then you extend this by as an algebra morphism, so by multiplicativity. And this defines a Hopf algebra, also has a star structure. Which determines which elements are, in inverted commas, real, i.e. elements of K, and which imaginary, i.e. I times K in this complexification. Okay, and this notation I've chosen to write it UQK complexified. Kenny used UQK with an R to indicate that it's real, but it's the same thing, confusingly. In a certain book that I wrote with Christian, we put an R up here instead of C down here. There are lots of different notations, but if ever you see a decoration with either a C or an R, it means that I'm considering the star structure. If there's no C or R, it's just the algebraic function. Okay, but I think I won't talk much about the star structure today. Okay, so the important thing, and Pavle mentioned this yesterday, the co-multiplication. Let's do is essential for tensor product of representations. Bears repeating, although you've probably heard it a million times, there is no way to define the tensor product of two algebra representations unless you can put this algebra into a copy of itself with a morphism, to a copy of D tensor D. There's no way of defining the tensor product of two algebra morphisms. So this is the way groups obtain their tensor product representations. It's by having this diagonal embedding, sending G to G comma G, which allows you to represent it on both of the representations in your tensor product at the same time. Q equals 1, this was co-commutative, meaning that if I flip these rules, nothing changes, with the consequence that V tensor W is isomorphic to W tensor V via the flip nut for every V and W. Again, this is no longer the case for UQK when Q is not 1, but it turns out it's not far from being true. And again, Pavle mentioned this yesterday. They are isomorphic, just not quite so easily. You do a bit more work. They're isomorphic abstractly, but you need to apply some correction. And the correction is probably should be a curly R, actually. Sorry about that. Tell you what that hat means in a second. But there's some explicit formula for this guy, which we'll probably get wrong. Check that. That is correct, amazingly. Though I haven't told you what XQ is. XQ is again some Q deformed version of the exponential function. Okay, well, it is what it is. Again, when Q equals 1, that's the standard exponential. When Q is not 1, you get some Q deformed version of it, which you can then apply to this operator here. You'll get an infinite power series in these operators E and F, which is why I didn't just take an algebraic direct product, but some completed direct tensor product, excuse me. But the important thing, as Pavle also said yesterday, is that of any particular power, there are only finitely many terms. So in any finite dimensional representation in which E and F act nilpotently, a sufficiently high power of E to the n or F to the n will always act as 0, so that in fact this action here on V tensor W will be given by only a finite number of terms in this expansion. Okay, it is what it is. This is part of what makes the representation theory of these quantized enveloping algebras more interesting than their classical counterparts. And allows for fantastic things like crystal bases, but that's for another day. Okay, so that's on the distribution side with convolutions. But we want also the function algebra. So for that, we're going to use matrix coefficients. Today, every representation is going to be finite dimensional and integrable, with a few exceptions towards the end. And a matrix coefficient of this guy is an element, or let's say a functional, linear functional of the form So we're supposed to be dualizing to go from distributions to functions. So we want things that pair with distributions. And I'm going to take exactly these guys here, which are given by V representation, psi a vector in that representation, on which I can make any element of UQG act, and eta an element of the dual. It's perfectly well-defined linear functional. If I were in the classical world, I could put not just enveloping algebra elements in here, but group elements. That would be totally justifiable, and I would obtain a function on the group. So the fact that I'm pairing it with my distributions is just the usual idea that you can differentiate functions. And that's exactly what I'm doing here. Okay, but in this case, I don't have group elements yet. I don't have group elements at all. So I'm just going to pair with my enveloping algebra guys. I get a bunch of functions, and then I'm going to define OKQ to be the set of all matrix elements of these guys, integrable finite dimensional representations. Very good. So this is some part of the dual of here. So it wants to be a Hopf algebra. This guy has Hopf algebra structure. If I turn coproduct into product, product into coproduct, et cetera, this should be a Hopf algebra. We just need to check that this particular subset of the dual is closed under these rules. And that's the following theorem. And maybe it's worth spelling a couple of these out. So the first thing to say is if you do this with UG when Q equals 1, UKC, you do get exactly the algebra of polynomials on the group SU2, where a polynomial just means a polynomial in terms of the 4 matrix entries of a 2x2 determinant 1 unitary matrix. And by construction, duality gives you exactly the standard product, co-product, etc., on this algebra of polynomial functions on our classical group. This really does look like a good candidate for polynomial functions on our quantum group. Let's give it a few of them explicitly if I, now there's one technicality. I think I'll put a little cop there. Often people flip one or other of the operations. So here I'm going to flip the co-product here and make it dual to the flipped co-product. This is not a big deal. Maybe I shouldn't have said anything. It's just a question of conventions and not everyone does that. So that I'm not saying anything false. Let me put that in. So if I have, for instance, eta 1 psi 1 times eta 2 psi 2, you can calculate what this means, and it's almost immediately, am I going to get this wrong now? I believe it's this way around. Where these are matrix coefficients for V and W, and this for W tends to V. Okay. That's the multiplication. And for the co-product, even simpler. Classically, what's co-product? It's given by restricting to the diagonal in G cross G. So it should be a function of 2 variables, G and H, on the group. So it should be this function here, this matrix coefficient applied to G times H. Writing that out, if I want to apply it to G times H, I can split it as follows. This function of G times this function of H, where this guy and this guy are dual bases. It's sometimes called matrix co-multiplication. This is the sum from I equals 1 to the dimension of V. And in this case, I don't leave the same representation. There's no Clebsch-Gordon formulas or anything fancy going on here. I'm staying within the same representation. This is called matrix co-multiplication. Because it is precisely dual to matrix multiplication. Did I want to give any of the others? Maybe I'll give, maybe I'll also give the unit element. It's just the unique up to scalar matrix coefficient of the trivial representation. Okay, and oh yeah, maybe I'll give the co-unit as well. So the co-unit is usually written as epsilon, sorry, and it's given just by actually evaluating like this, the obvious thing. A remark on this issue of matrix co-multiplication is that I can write my OKQ as the direct sum of, so here I've allowed any integrable finite dimensional representation, irreducible or not, which is good because it allows me to add two functions to get a matrix coefficient of the direct sum representation, or multiply to get a matrix coefficient of the tensor product representation. But I could also reduce it to a basis, there's some redundancy here, and take it as a matrix coefficients of the irreducibles, because I can decompose any other finite dimensional into irreducibles, as we saw on Monday. And this, another way of writing this would be to put it as the dual of the endomorphism ring. Any matrix on VM, I can stick into this slot and get a complex number, and that's precisely the dual space to these matrix coefficients. If you're a physicist, all you do is you take your bra and ket and you move them to the other side, and you get the dual, which is now the endomorphism ring. Why a physicist's life is much easier. And the co-multiplication that I have here is precisely the dual to the multiplication element by element that you have over here. Seem reasonable? Any questions there? So the pairing that we get just by the fact that these guys are dual to each other is the analog of differentiation at the identity element in the group. But we might want more general distributions. Like I say, these are only the distributions which are supported at the identity. Maybe we also want distributions supported globally on our group. That is, to produce a convolution algebra. Certainly, if we want to do Quantized duality, get my mathematicians right. If we want to do Quantized duality, I need more than just the enveloping algebra. I need the algebra of distributions, at least some algebra of distributions on the group. Let me call them polynomial densities. Distributions on the group that are given by a polynomial function times the measure, R measure, which we haven't talked about yet, but in the classical case, that's what it'll be. It's an infinite direct sum of finite dimensional matrix algebras constructed precisely to be dual to this in the weakest possible sense. Okay, so the full dual of this guy includes infinite direct sums. I just want those that are finite direct sums. It's like taking finitely supported distributions, densities, if you like, compactly supported densities on my dual group. Compactly supported in the phase space, I should say. Again, theorem. Okay, so this sits inside OKQ star, and yeah, and it is what it is. But this is also and now I need a technical word. keep things coherent, I'm going to make it dual to the opposite multiplication, just like before I made it this guy here dual to the opposite co-multiplication. That's a technical point. The nice thing is that we get precisely a Hopf algebra again with one technical point. This lands in the multiplier algebra of these guys. And rather than explain in detail what it is, let me tell you concretely what it is. So it's guys in the direct sum of all possible tensor products of endomorphisms, which are row and sum finite. Sorry, row and column finite, excuse me, what it is. And let me just say, for saving time, what row and column finite means orally. What it means is if I fix any particular m, then there are only finitely many terms in this direct sum, the image of my element, which contain that particular end Vm non-zerally. And likewise, there are only, for any particular m prime, there are only finitely many non-zero terms in this direct sum, which contain that given end Vm prime non-zero. So if you like, it's like a diagonal. You know, a perfectly good example would be something that sits in the diagonal of this guy, in which case it's one term in every row and one term in every column. But I allow things to have more and more rows and columns as we go out to infinity. I just don't want any row or any column to have infinitely many. And if you think about it, if I multiply one of these guys by something which is finitely supported here, I'll get something else which is finitely supported here. So this is why it's called the multiplier algebra. Okay, and so this is a whole theory which was developed by Alphonse van Dale, which is very beautiful, called algebraic quantum groups, which can be used to model, for instance, discrete but infinite groups. So a discrete but infinite group like Z, you might consider the algebra, convolution algebra of finitely supported elements, and you'll get something which behaves just like this. Okay, with the coproduct being no longer finitely supported, but finitely supported in any particular row or column. Right. Okay, so now we have two versions . Two versions of distributions, one version of functions. But I gave a whole list of things at the start of other things you could do. So for instance, you might ask for C star on this side or for C on this side. These, of course, are analytic completions. So for that, we need an L2 space. So now we pass from algebra to analysis. Maybe a good time to pause and ask if there are any questions. Really don't need much analysis in this whole story. Sort of a running gag amongst my friends that I've started dissing C-star algebras, given the fact that I grew up a well-educated C-star algebraist. There are a number of things that C-star algebras are extremely good for. But when it comes to representation theory, ultimately, you almost always need to work with some dense subalgebra of your C-star algebra. So for instance, Dixmier, towards the end of his life, stopped thinking about C-star algebras and started thinking about universal enveloping algebras because he was trying to apply his C-star algebraic theory to the theory of semisimple Lie groups. And to do so, he realized that just knowing abstract facts about existence of Plancherel measures, for instance, was not enough. You actually, sooner or later, need to get down into the nitty-gritty, do some algebra in order to be able to prove your facts about C-star algebra. So in fact, even the things that I'm about to tell you now, you could do without much discussion of C-star completions, Hilbert completions, and so on. But since it's a familiar language, it's very useful to phrase things in that way. So if we're going to do anything analytic, the one thing we need is a Haar measure. I really want to call this integral, but it just starts to look ugly after a while, so I'm going to call it mu. But I want to call it integral. It's a linear functional on opaque Q, and it's given by the following formula. It takes this constant function 1 to 1, so it's a normalized Haar measure, and any other matrix unit for any non-trivial representation will be mapped to 0. Okay, just like in harmonic analysis on the circle, the only harmonic which has non-zero integral is the constant one. Exactly. So that
it looks like the representation that I mentioned.
Yeah. So this works for any what they call co-semisimple Hopf algebra, Hopf star algebra, in the sense that anytime I can write my Hopf algebra.
No, but you're thinking for I'm trying to say that there is a more general notion, right?
Yeah, you can define this in general.
Okay,
and to prove the existence of such a thing, you need to do some algebra. But yeah, so let me. No, you're exactly on the right thing. So first of all, this is called the Haar state, or the Haar measure, or the Haar integral. Let's go with Haar integral. And satisfies the properties that Rita is trying desperately to tell us about. The following two properties. The first is left invariance, or left and right invariance, in fact, in this case. So how does this work? This works that if I integrate just the second variable of a function of two variables, then it doesn't depend on the first variable anymore. If I integrate a function gh with respect to h, the g that I chose is completely irrelevant. It's always going to give the same value. I see why Ray is looking confused. That should be mu. Much better. And the same on the right. Okay, so that's left and right invariance. This time I'm thinking. Yeah, so this is unimodular, and this is the case always for compact, and in particular for these co-semisimple. Sorry, I'm preempting your. Yeah. So I concur wholeheartedly with Rita. And the other one is, wait, what's the other one? Oh, positivity. What this means is we can use this guy here to define an inner product. Or if you like, you can use the GNS construction to produce a Hilbert space. When should I finish? 10 minutes. Okay, so the point is that this Haar integral brings us all sorts of joy. So we can do the GNS construction. We now have a Hilbert space. And this Hilbert space comes with left and right multiplication actions. In the classical world, these are the same. These things are commutative. Here, they're different. But the point is that these act boundedly so that I can define the C-star algebra completion. So now I have continuous, not C-star, C. Continuous functions. It is a C-star algebra, but it's just to be seen as continuous functions on my compact group. I also get convolution actions. Oops, what am I doing? I need to go fast. Feel the clock ticking. No, try again. This one here requires a little bit of explanation. Since I have this linear functional, I can turn functions into linear forms on my functions, like this. I'll call that the Fourier transform. Fourier transform is a bit of a stretch here because there's no dual group yet, but let's just go with it. And the point is that this extends to an isometry what do I want to say? I didn't do that very well. No, let's just leave it. Let's just leave it. I'll be vague about that. Does extend to an isometry, but I haven't defined the dual integral yet. But for instance, I can take an element here. I can Fourier transform it. It's in this dense subspace. I can Fourier transform it, act by conjugation, and then re-Fourier transform it to land back in here. And it turns out that that will be
a bounded action here, while it's an unbounded action here. In short, the Fourier transform allows me to blur the distinction between a function and a distribution at the level of L2. Okay. And so as a consequence, I can define my C-star algebra as the operator closure of my convolution algebra of distributions. You might, sure. Yeah. So yeah, maybe it's worth pointing out that this is a theorem that it does land in here. The only thing that's clear is that it lands in the dual of OKQ. But in fact, it lands in here. And this is again where the physicists come into fore, because it's basically given by up to some finagling by switching Bras and Ketz, so that my matrix coefficient becomes an endomorphism here. Yeah, also that's the other way that you could do this, is you could take the coaction here. Yeah, in fact, maybe that's a better way. So yeah, excuse me, I should not have, I think I jumped the gun here. So, thank you, Paula. Would have been better for me to have written. So I want to do, if it's on that side, F1, X paired with F2. And here, if I do it on the other side, I'll do X paired with F1, F2, where I'm using Wheeler notation with a co-product. I should have done that from the start, I think. Would have been much cleaner. But it turns out to be equivalent to do it this way. In any case, I wanted to talk about the Fourier transform, so it's convenient that I introduced it. I just did it out of order. This was probably better to be contained in 3. And then 4 is there also exists a Fourier transform which exhibits an isomorphism between OKQ and DKQ in this way. And I think I should stop, but I wanted to at least state Poincaré theorem. So remember what the Poincaré theorem is supposed to do. The Poincaré theorem is supposed to tell you how to decompose L2 of K as a direct sum of irreducibles. And this is what happens. I'm calling it Poincaré. A better name might be, well, Peter Weil is one thing you could call it in the right interpretation. Or sure orthogonality, which is again the same thing written differently. And it's the following statement. I'm going to explain what this is in a second. Okay, in short, this is endomorphisms on VM. I say that to begin with, and then tell you what the appropriate norm on it is. Endomorphisms on Vn have actions of dk on both sides. On the left, by composition with the representation, or on the right by composition with the representation. So it's a double DKQ module. And I can take the direct sum of all of these modules. This is also a double DKQ module, as we observed here. And the two are the same. They're isomorphic, and they're isometrically isomorphic, as long as I put the right norm on here. And what is the right norm? This curly L2 is supposed to look like a Hilbert-Schmidt norm, because that's what it is. But it's twisted, the quantum. And it's given by the following thing. So if I have two matrices, it's going to be given by the trace of, let's get it right, T star S times our favorite Q to the H, where Q to the H here means the representation of K on this particular representation VM. It's a positive diagonal matrix, so that this will in fact define a positive definite form in a product. And I need to divide by, let me put it under here, the quantum dimension of VM, where the quantum dimension of VM is just the trace of the identity operator, right? The classical dimension is the trace of the identity operator, but I want to take the quantum trace this way here. I believe I'm now out of time. So the philosophy is we get exactly the same formula as in the classical case. The L2 classical functions on a compact group are given by a direct sum of d squared copies of every irreducible representation, where d is its dimension, with an inner product given by the Hilbert-Schmidt norm, renormalized by the dimension, square root of the dimension if you want to talk about the vectors. And in the classical case, what you get is just a sum of traces. Here, you get some kind of modular function. So the modular function is occurring now not as a function on the dual group, Plancherel measure, but as a family of matrices, a family of finite dimensional positive matrices. So our Plancherel measure, if you like, is no longer 1 over the dimension square root of the dimension on each of the finite dimensional representations. It's 1 over the square of the quantum dimension times a non-scalar matrix. Right? So the moral of the story is, in the world of quantum groups, even for unimodular quantum groups, you can get a positive definite matrix appearing in your Plancherel measure as well as just a function. And I'll stop there, and we'll see a similar phenomenon with the compact semisimple Lie groups, quantized semisimple Lie groups on Friday. Yeah.
Thank you, Robert. Other questions?
Yeah. Yeah, you could, this is also totally valid as UKQ, yeah, sorry, UQK by modules, just because as long as you know what the DKQ representations are, you can deduce what the UQK modules representations are, and vice versa. So you could easily describe it in that way as well. Yeah.
Is there some an algebraic direct sum or?
Ah, thank you. Yeah, I did not say this should be an L2 direct sum, so that it's a Hilbert space. Yeah.
Okay, please don't rush. I don't know the announcement. Let's thank the speaker again.
So